Hello everyone, welcome to my class project for Nonlinear Dynamics at Control. The paper I chose to study is titled Behavior Trees in Robot Control Systems. I was motivated to start this problem because I really enjoyed examining this simple feedback control loop for low-level control. I think systems theory and control theory really gives us qualitative tools for this kind of analysis. We're really familiar with how to analyze these systems, particularly for linear systems. But really, these systems are kind of constrained to low-level control, like if we want to control torque or move position or things like obstacle avoidance. So now thinking about the higher level feedback loop of planning and control, if our why desired is some really high level goal, like go to the kitchen, fetch me an apple, I was really interested in how can we apply some of the principles from systems and control theory that gives us this kind of qualitative analysis of convergence, error. How can we apply those same principles to high-level planning and control algorithms that are composed of these lower-level controllers? So that's really the main problem that this paper is trying to address. They present this framework, behavior trees, it's a framework for organizing high-level decision-making process into these smaller scope kind of local control loops. And they try to attempt to answer the question, how do you provide these mathematical convergence and safety guarantees for specifically for applied robots? So in this talk, I want to go over what is a behavior tree, how are they defined, and two important sections of convergence, control barrier functions within behavior trees, and finally, I put this all in a simulation where theory kind of met reality, which I want to show you. So the first question to ask is really, what is a behavior tree? And it's a task switching structure, which is given an objective and this set of actions, a behavior tree answers this question of what to do next. So let's say we have an objective, we have a setting of a robot in a maze and it wants to find a blue object. That objective is to navigate in the maze and find a blue object. And all these actions can be apply torque, rotate, drive forward, process this image, find a free path. These are all actions, and this behavior tree we'll see will compose all of these actions intelligently, kind of hierarchically, in order to achieve that high-level goal. It'll break down the high-level goal into sub-goals and apply those actions in an intelligent process. So just kicking off with some definitions, a behavior tree is going to be this pair of control and metadata. And the control is what we know as control, some vector of control. And metadata is really this kind of indicator variable that will tell us if that tree is running, successful, or has failed. And within that behavior tree, there's a notion of a state, and it's up to us to define what our state variable will be. Now, within this behavior tree, we can see these local dynamics evolving, and a control policy, that may be of a function of x, evolving within this behavior tree. Within this specific behavior tree. So now behavior trees are composed of different subtrees. The first one can just be a condition. It could just be if it's formally defined that this condition is not running, it's just either true or false. The next can be sequence, and really what this means is if a tree is composed of two subtrees, then when X has succeeded in tree 1, then we're now running in tree 2. Likewise, for a failure, when X has failed in tree 1, we're now running in tree 2. So now, really what we're getting to is trying to view this through the lens of dynamical systems and control. We define this really important definition of an operating region. So again, we tried to partition subtrees into their kind of local dynamics. And really this operating region will really capture where that those local dynamics are occurring. So the operating region is formally defined as the intersection of an influence region and the region in the state space where the dynamics are currently running. The influence region really represents previous conditions that need to be held true, and we'll see that later. And of course, where the dynamics are running is where this local dynamical system is occurring. So the state space, is partitioned. The entire state space is partitioned into discontinuous dynamical systems, and as the robot is moving, as an agent is moving from operating region to operating region, we can think of that as transitioning between operating regions. And the authors make a really strong note about the existence and uniqueness of solutions within each operating region and also for the entire behavior tree. So the first topic that we start to see an intersection of dynamical systems and control and behavior trees is this concept of convergence, which is basically, will we achieve S naught, which is our root node success? So the authors cast the concept of converging to a stable equilibrium point as equivalent to satisfying the highest level behavior tree goal. So after the state space is partitioned into operating regions, this convergence analysis asks the question, when we start from some particular operating region and we transition between operating regions, do we finally end up in S naught or S0, which is our high level goal? Formally, that's written in this convergence theorem. And it says that given a behavior tree in some external constraint region, which is just kind of a recursive formality so that we can apply this to sub trees. And this level of abstraction, which is the hierarchy of trees, the theorem says that if we stay in a tree for only a finite amount of time and we transition from tree to tree, then we will finally end up in S naught. So again, the state always starts in omega 1. There's a finite time that we stay in any omega, and we do transition to the next omega. And as we progress through the operating region, we don't violate previous conditions, and we will always end up at our goal, which is X naught. Now, there's a small caveat about probabilistic transitions. If we're not certain exactly how we'll transition or when we'll transition, and I outlined that in our report. So this next topic is behavior trees and control barrier functions. And control barrier functions is a tool to synthesize controllers that satisfy hard constraints. And we'll use this to design controllers within a specific region to guarantee the state is always safe. So the main idea is to use a control barrier function to prescribe a control law within each local dynamical system that satisfies the current desired conditions and doesn't violate previous conditions. Formally, the definition of a control barrier function is given here, and all it says is basically a relationship between control and the edge of some function that we care about, primarily our barrier function h, and our control will throttle or limit the control effort into the dynamics such that we can never push past that barrier h. So shown pictorially, we assume that each condition can be formulated as a scalar function h, and satisfying a condition, we know it implies achieving some sub goal, and which implies we're always guaranteed to keep the state safe. So a CBF specifies a control law that always satisfies a condition. So I put this all together in a simulation using Ross and Gazebo. There's a behavior tree composed of 3 subtrees: get location from Q, go to pose, and finally look for an object in that pose. I think this is really fascinating to see the kind of concert of high-level planning from going to a location, creating a plan, and low-level control to moving motors forward, etc., all kind of working harmoniously together to ultimately find an object. All the details of how the state space is partitioned into different operating regions is outlined in the report, and a note on when and how it will converge is also in the report. Thanks so much for listening. Please let me know if you have any questions.